So this is going to be a status update on the project we are internally calling ICL1, hence ICL 0.5. It's a joint work that I'm doing with, well, Dan, Edmund, where's Matt? Oh, Matt just left. Right, Liam, who's not here, and Susan, who's not here. Okay. Right. So I want to start where we left off at the June-July meeting. We had a few basic questions about the viability of developmental interpretability, and those were, do transitions actually exist? Can the theory make contact with reality? Do the transitions predicted by learning theory actually exist in real-world neural networks? And there was a question of, even if they exist, can we detect them? Can we build tools that scalably detect where these transitions occur? And last, can we understand the transitions? Can we say something about the structure forming during these transitions, the link between circuits, that's even the right framework, circuit formation, and phase transitions? So today I'm going to be presenting some early positive updates on each of these questions in a specific context of this family of regression transformers, which I'll explain in a bit. So in this context, yes, transitions exist. There are a bunch of them. We can find them using tools from SLT. Some of these transitions don't seem to be visible from the loss, so you need insights like the learning coefficient to find them. And we can understand them. Right now, that's still very much at a manual, mechanistic interpretability level, so it's not automated in the sense we would hope for eventually, but suggestive evidence for the link between structure formation and phase transitions. Again, in this specific context of these linear regression transformers. Okay, so my particular aim is going to be to explain, there we go, the things you see on these animations. So, this weird plot over here where we're moving around, these things over here, the regions down here, all these different plots. Right now, it's supposed to be a mystery to, kind of tempt you to stay. Okay, so we'll get back to that later on in the presentation. Okay, let's take these questions really one by one. Do transitions exist? Can we detect them? And can we understand them? So, right, before we get into this particular example, I'd like to put it in the context of some of the other projects and some of the other research going on. So, right, that's this Bayes versus to SGD point. Right, in my head, I imagine this axis from theory, I don't know, maybe that's the gray book, pure mathematical theory, all the way up to applying things to GPT-N. One important point on this trajectory is making contact with SGD. And so I think the work done on TMS takes us, pretty far along this towards, hey, maybe these transitions aren't just nice theoretical things, but they actually exist in real world systems. So often, going from theory to toy systems is as big a jump as going from toy systems to larger systems. At least that's being optimistic. I'm being optimistic.
TMS to GPT-4.
No. This is called optimism, like self-deception. That's right. Anyway, so the question is, how much further can we go here? Right, we have some suggestive evidence already from work done by Anthropic's team on induction heads and in-context learning. Right, so here I'll use in-context learning to refer to any process by which the loss decreases with the number of tokens. It's a very general notion. Some people take a more restrictive notion. What the Anthropic team found was that there's this intimate relationship between the formation of the structure, these induction heads, which are doing something like token by token modus ponens. Right, you see A, then B, then you see A again, so you should predict B. Right, so there's this relationship between the formation of the structure and a transition or a sudden improvement in the ability of these transformers to do in-context learning. Okay. And this is macroscopic enough that you can actually detect it in the loss. So you see this loss bump. Now, this actually shows something that we expect to be true more generally as we go to larger models, that like even if there is a transition taking place here, it's pretty subtle, and you don't immediately see it. And you might have to go to higher order derivatives to actually see the transition taking place. And something that's true more generally of phase transitions is that often transitions are more legible, they're easier to read in higher order derivatives of the observables we might care to measure. Okay, so why care about ICL? This isn't just an interesting validation. It's not really a validation yet. We still have to apply the SLT machinery to this, which is another ongoing project. But why care about ICL, not just as a validation of DevInterp and SLT? Why is it interesting from an alignment perspective on its own? Well, first of all, ICL and emergent optimization more generally are scary because they erode control. If you can't predict when capabilities emerge, when goals and values emerge, it becomes harder to constrain the system and prevent it from doing things you don't want it to do. But on another point, this is maybe an underappreciated point, is that ICL poses a fundamental barrier to interpretability. At least the way a lot of people are thinking about interpretability is that you're trying to look for circuits in weights, right? Depending on how much of the internal computation in advanced models is due to in-context learning, this might be wrong. Maybe you find that the only things implemented in weights are little SGD modules, little optimization modules, right? And you can't make sense of the behavior of the model in terms of these internal optimization modules. You have to go one level up. You have to do interpretability at the emergent level of these in-context learned circuits. And on a deeper point, right, most of the theories for how interpretability caches out are in terms of, and then you read its reasoning process and you see if it's being deceptive, and if it's being deceptive, you hit stop and you, fry the weights or something.
Wait, is this an actual hypothesis that somehow inside the neural network there's like these SGD modules that are just emerging?
Those things exist. Yeah, they exist. Yeah. And induction heads are a very basic example like this, but the models we'll look at learn the versions of this, or are able to learn versions of this. So ICL may be inseparable from reasoning, right? Interpretability caches out in our ability to actually read the reasoning process. It's not enough to read off, these internal representations were activated. We want to know what kind of computation is taking place. And in-context learning could be a fundamental component of that. So understanding it gets us closer to the hard problem of interpretability, which is understanding internal computation. Okay. Right. So what we're going to look at in this talk is this particular kind of simplification, maybe a toy setting in which to study in-context learning, which is in-context linear regression. It'll take us some part of the way up to GPT, and still on a logarithmic scale, okay? Right, these models are now tens of thousands, maybe hundreds of thousands of parameters. Toy models of superposition were in the order of 10. So we're making strides. Right, how many more orders of magnitude left? 3 more jumps like this, and we're there. In any case, let me explain this setup. So we have some inputs X, some outputs Y, and tasks W. Right? The inputs are sampled from some normal distribution, some d-dimensional normal distribution, and the Y's are scalars. The Y's are generated by taking the dot product of these task vectors with the inputs. So we're just computing the projection of X onto the line span by W. Okay, and then we add a little bit of noise just to make it a little more difficult for the model. Okay, so we flatten these. We pass them into our transformer one by one, so an X, a Y, an X, a Y, and so on. And then we train the model to predict the Y's for each of the X tokens. Right, so this one is supposed to be as close as possible to this one, and so on. Yes?
So the entire X is a single token?
So the entire, yeah. So this is 4-dimensional input, 1-dimensional input. These are put together into a 5-dimensional input. So the first component of that 5-dimensional input will be the y's, y 0, 0, 0, 0, and this will be 0, x1, x2, x3, x4.
So how many residual stream vectors are you going to end up with?
The residual stream has 64 dimensions.
So that's the dimension of a residual stream vector, but is it one residual stream vector per component of that?
64 times 5.
61 is 5, okay.
Okay, when we train this model, we're not training on just one task, we're training on a bunch of different tasks. We're training on up to big M tasks. So what earlier authors, I'm talking about Reventos et al., looked at is how does the learn transformer vary as you change the number of pre-training tasks, this task diversity M. What they find is a transition between two different kinds of algorithms as you change M. So the important thing here is this orange line is close to the green line for low M, close to the blue line for large M. You don't need to understand much more than that. What's happening is for low M, you can memorize the tasks, right? You can just say, oh, these specific 10 tasks showed up, I don't need to memorize anything else. If you have many, many tasks in the pre-training distribution, then the best thing you can do is to actually learn the generalizing solution. And you see this as well in lambda hat estimates at the end of training. Right? So it's much simpler to only memorize 2 or 3 tasks than to learn full-on linear regression. But as you increase the number of pre-training tasks, at some point you converge to an algorithm that's independent of M, independent of the number of pre-training tasks.
Well, then to be clear, Reventos et al. Weren't measuring that.
No, this is us.
Sorry, what are the different curves?
So the different curves are just at different numbers of SGLD steps.
Just ignore them.
Yeah, just
Pay attention to the yellow.
yellow, yeah. Okay. Okay. So if you look at the loss curves for these, it already suggests that there are 2 transitions. So you see this bump here, right? And so if you plot the slope, you see that there are these two peaks here. It already suggests that, hey, there are at least 2 interesting things happening during the training process here. Yeah, this won't be the same induction bump that we see in the language model case, so it'll be something else. Okay, so yeah, even looking at the loss in this case, it seems that the transitions might exist. Maybe we can find more in a little bit. Okay, so how do we do this? Let's go into the theory for a little bit. Talk about some of the different approaches you might take to detecting transitions. Review the different types of transitions, which Dan already talked about. And then talk about 2 specific techniques for trying to detect these transitions. Okay, so broadly I think of there being 2 approaches to detecting transitions. There's a supervised approach, where maybe you already know ahead of time what the model is learning. So this is like the progress measures approach. You know that this structure exists at the end of training, so you can construct a manual metric that tracks how close that structure is to being fully formed. But that requires you to already know what's happening, what the model's learning. What we really want are unsupervised metrics, ways of detecting transitions where we didn't know there was one beforehand. So in reality, these are complementary, but what we're trying to do with the tooling from SLT is really this latter category. Okay, yeah, and just a little more. So for example, this in-context learning score that Anthropic's team looked at probably falls into the former category. They know that it already has something to do with in-context learning, so they come up with a score. Whereas looking at the loss, or the derivative of the loss, is more in the second category. Okay, so types of transitions. Okay, one equation in in these slides. We've already looked at these type A transitions, right? Where there's competition between the first 2 terms in the free energy formula. And for type A, the loss goes down as the complexity goes up. If you look at high order terms and you hold the loss fixed, then there can be competition between the lower order terms. And here this has a log term, but we'll treat it as a constant. Okay, so just looking at this, there could be a transition where lambda goes down, but C comes up for fixed Ln. I think when Dan wrote this down on a piece of paper, he was thinking, oh, this will just be fun to include in the slides tomorrow. No way, this is real. But I don't know. We might be seeing something like this in this ICL case. Okay. So I'm just going to illustrate two techniques we're looking at. One is actually something that the Anthropic team already looked at. So that's this PCA technique. What they do is you take a batch of a bunch of samples. You run it through your transformer and you obtain a bunch of logits. You stack those logits, and so now you have one giant vector that kind of acts as a functional proxy for your model, for that batch of data. You can look at how that vector changes over training time. And then you can do PCA on that vector to obtain a much lower dimensional representation of its training dynamics. So that's what you see here. And you see this kink associated to this induction bump to the development of in-context learning. At the time, it was kind of introduced in an ad hoc way. There's no principled explanation of why this might be a reasonable thing to do. But really, there's a reason that something like this would work. Right? So we know from dynamical systems that dynamics are determined by the critical points, separatrices in your phase space. And so if we have a trajectory starting down here, moving up here, and then moving away from the singularity again, you project that down and you see a kink here. You see some kind of change in direction. Now, you have to be careful with this, because projecting down can also introduce kinks where there are none. But in general, you see a kink in the PCA plot, suggests there might be something interesting going on there. Okay. And then there's this other technique. So based on lambda hat, this really should be a hat. Okay, going back to a picture from the TMS presentation. If you remember, this is the plot that shows the proportion of different k-gons as you increase n. So this isn't a Bayesian setting. One thing you could do, it's very naive, is we know what the lambda hat values are for each of these curves empirically. So you can estimate, or you can calculate the average lambda hat as a function of n. Right? You take the proportion of k-gons in this phase, multiply that by the associated lambda hat, add it to the proportion for this phase times lambda hat for that phase, and so on. And so you get this blue curve. And so this is a proxy for what you're actually obtaining with local lambda hat estimation. It's not actually the same thing, but it's a similar way of thinking. What you notice is that this thing changes smoothly. Right? There are no sudden jumps, and it's only when you look at the derivative in red that all of a sudden you see peaks precisely at the moments that you see transitions between phases. So this is the same general principle of look at higher order derivatives to detect transitions more markedly. Okay. So what happens when we do the same thing to these in-context learning transformers? Yes?
Can you recall how do you get these proportions?
How do you get these proportions? Remind me.
So,
Yeah.
So for each of these phases listed on the right-hand side, take e to the minus theoretical free energy of the phase at that end, take all those exponentials, and then normalize them so they form a distribution. That's a function of n. This is a plot of those distributions. With
theoretically predicted losses and empirically estimated lambda hats.
So these are the occupation probabilities. That's what we have.
Occupation probabilities.
It's really only worked asymptotically, but it kind of works.
Yes.
So to do this, what do you need to know about the... So you need the theoretical values of...
You need some estimate of lambda.
Lambda and of the DNA.
And of those, yeah.
Yep.
And be able to put them into balance.
Yep. Okay. So this is loss, slope of loss. This is lambda hat, and then slope of lambda hat. Right, so the important thing really is what's happening here. When the loss is roughly constant, it's already sort of reached a threshold, a plateau, you see that lambda hat comes down. Okay? If you look at the slopes, you see in this inset where we've zoomed in on this later part of training that there's this peak downwards, this spike where this transition is happening. Now, if you look at the associated place here, there is sometimes a bump in the loss. So sometimes this transition also involves the loss. But for low m, it's almost invisible from the loss, and you see it pretty much exclusively in terms of lambda hat. So, type B transition? Maybe. We need to do more tests, right? A natural thing to do would be to now see if the ordering of the transitions we find here respect the ordering you would get from the free energy formula. We'll get into there. Yeah.
My understanding of the top left graph is that each of these curves is with a different m.
Yes, different m.
The lower ones are low m, right?
Lower m.
And so for small enough m, you don't see the second type of phase transition. But you're saying that
You do see the second type of phase transition, but the loss doesn't reveal the transition.
But it is still there. So
Yeah.
if you disagree with the original paper, which said that you only get a second phase transition when you have large enough n, you're saying you actually get it all the time, which is hard to tell.
There is no.
There was a different transition.
Yeah.
Maybe that was something Jesse skated past. As you increase in, the model found at the end of training switches from one element to another.
Yeah.
Now he's talking about over
Yeah.
the course of training.
But for all of these m,
So,
if you train long enough, you'll get to the fully general thing.
no.
Is this phase transition not the one where you go from the memorizing each W to learning the general thing, or is it just it's not that phase transition?
Well, it's maybe related, but we should think of
Go
it
back
as
here.
separate for the purposes of this.
Right, let me come back here for just a second.
Yeah, sorry.
Yeah, so the transition was originally in this hyperparameter m. We're interested in transitions over time, over SGD time. Now it's natural to think that there might be some kind of transition in this intermediate regime, where maybe at first it learns the generalizing thing, and then eventually it memorizes, because it sees enough examples that all of a sudden it can justify memorizing. And that would be associated with an increase in complexity. We still have to do that. So we don't know yet. Yep. Okay. Anyway, so there seem to be additional transitions here. Right, and I'll argue that what we have here is actually two different transitions. Get to that in a second. But that means that maybe we can actually detect transitions, right? I think when we started this out, we thought, okay, loss is going to change smoothly. You won't be able to detect transitions in the loss. Lambda hat will change smoothly. You won't be able to detect transitions in lambda hat. Maybe these tools are actually a little more robust than we gave them credit for. Okay, but can we understand what's going on here? Here, I'm just going to focus on this low m limit, the low task diversity limit where it's memorizing. But even when it's memorizing, you see more examples and you can get better at recalling the correct memorized task. Because retrieving it, you need evidence from the samples you've seen. Okay, so let's look at the M1 transformer, the simplest possible thing. Okay. So what we're doing here is we want the transformer to do something that you would think a transformer can do, which is multiplying two vectors together. Right? That's all that's going on here. We have one task, so all the transformer ever has to do is matrix multiplication. Okay. On the very left, we have the PCA plot with the first three components. This was developed in the same way that I described for the anthropic PCA plots. Then we have loss, lambda hat, and weight norm. Because as recall from the type B transitions, the type B transitions involves an increase in the lower order terms, in the C, which is related to the prior, and so related to weight norm. Okay, so top is the values themselves, and then bottom is the slopes over time. And you see that I've colored in a few different stages, which are called zeroing, task acquisition. Then these two are involved in input generalization. I'll explain actually what seems to be going on in these stages in a little bit. Okay. So I'm gonna play the animation now. So I would pay attention to the PCA plot on the left first. You see that orange is going up, turns the corner as we move into stage 2. Now, as we go into 3, it turns the corner again and moves away. And we reach the end there, right as we're about to go past 100,000 steps, and then there's another transition that you can't see here, but you can see in the weight norm over time. I feel like a sports commentator. Okay, I want to do that one more time. Okay, so in the first part, loss goes down, right? And we see this weird change in inflection. Boom, loss goes down, reaches what seems like to be a minimum. So at this point, it's learned the task, and we don't know what's changing. Here, lambda hat comes down and reaches a new threshold. And then here, weight norm starts increasing rapidly. Okay, so what's happening here? Okay, so so for zeroing, this isn't very strong, but what seems to be happening is that it's moving closer to predicting zero, right? Which is the average over all possible inputs. So it's a seemingly sensible thing to do. During the second stage, it actually learns how to implement this. By the end of training, it'll implement this transformer pretty much entirely using the embedding and the unembedding, right? So it uses the embedding to perform the actual matrix multiplication, and then uses the unembedding to read that out from one of the residual streams. Okay, so what's happening in this green stage, right? Well, well, let me explain what's going on here. So, I'll explain why you need this for the M2 case. But what's happening here at a behavioral level is that the model is somehow generalizing to large inputs. So if you have a very large input, there's a layer norm term somewhere in the model that makes just doing a linear transformation difficult. So you need to modify yourself a little bit to get around that. And at some point, the model figures out that it needs to send its activations to some large values to get around the layer norm. And the performance on larger inputs than it was sampled with, so if you take a normal distribution that has a larger scale than it saw initially, the performance on those starts to improve. So that's what you see happening in these later stages. Okay, I guess we can look at this. So that's related to what's happening in the embedding. So that's the plot here. So what we've done here is we look at so the embedding matrix is 64 by 5. 5 for the input token dimensions and 64 for each one of the residual stream dimensions. What I've done there is projected these 64 5-dimensional vectors down into 3 dimensions. So we're going to watch how they behave over time. Oops. Okay, this takes a second to start. So it'll be kind of small. You have to zoom in, right? Seat of your pants. You see that at the start of the green one, it collapses onto a line. Oh, it's not actually playing. Oh. Okay, here we go. Okay. It's starting to move. Transition 1, transition 2, and now squeezes out, pulls apart, collapses on, and starts increasing in scale, and devolves into chaos. Well, but it's still very tightly ordered chaos. Okay.
So what exactly is this proposal in this case? It's not the same as on the left?
No, so again, this is for the embedding matrix.
Yeah.
We've got 64, you can interpret it as 64 5-dimensional vectors that we've projected down into 3-dimensional space. So we've got 64 points. I'm going to leave some of the speculation for why this is until the discussion, because Dan berated me. But, so stay for that, I guess. Okay, so let's look at the M2 transformer. Okay, how am I doing for time? I've got plenty of time. Okay, so M2, what is it trying to do? Right, so what I've plotted here is 2 weight vectors. The 2 weight vectors span a plane, a 2-dimensional subspace of this 4-dimensional input space. Okay, and X we only care about the projection of x onto this plane. The other components don't matter for the sake of making a prediction using these two tasks. In particular, we're going to want to predict either this projection or this projection, depending on whether we're currently in the task 1 stage or the task 2 stage. And so it has to figure out from the given examples which one of those two situations it's in. Okay. All right, so same graph that we saw before. Again, 3 stages. What I really think is happening here is that this green is subdivided into 2 additional transitions, and there might be extra ones somewhere here late in training. Okay, fine. There are 2 transitions in the in the green stage. Yeah, so same plot, and let's look at this one. Okay, so in training, moving along, we go around the first bend, we go into the second bend as we enter this green stage, going up in the weight norm as before. So this is very similar. A few differences from the preceding one are there's a more marked change in inflection here. What else do I want to say? That's really the main thing. So yeah, so the loss, the first 2 stages are a little different than in the preceding case.
Maybe it's worth saying that Jesse stared at weights for weeks and came up with these stages before we plotted like the lambda hat.
Right. That's good. I'll repeat that. So these stages are really done from all the mechanistic stuff that I was looking at. You write it, and then all of a sudden you see that it matches the lambdas and losses and these inflection points very well. Okay. So I've called them, given them different names: midpoint acquisition, task acquisition, and input generalization. This is the same as before-ish. This is relatively the same as before. This first stage is a little different. Okay, so what happens during the first 2 stages is that the model seems to learn the task. Okay? For most of the tokens, especially the early tokens, the loss kind of reaches a plateau and it stays there for the rest of training.
You should explain the graph, what's in it.
Yeah, I'm jumping ahead a little too much. This is just loss. I'll get to these in a second. Focus on this one right now for right now. Each of the different lines are a different token. So from 1 to 8. And then there's an orange line which represents the mean loss, which is the thing we train over. Okay.
Is each sequence the same way?
Yeah, 8 examples, so 16 tokens. Because it's pairs. Okay.
Only make a prediction on the odd number tokens, right?
Yeah, exactly, only on the, yep. Okay, so during the first stage, the loss sort of reaches a plateau for most of them. For later tokens, loss keeps going down. Okay, and slightly down. Okay, so what's happening during the first 2 stages, or what's different from the first stage to the second stage? During the first stage, what it seems to be learning is to predict using the average of the 2 tasks. Right? If you sum or you average the 2 tasks, you get some vector. You predict that. The prediction using that is the best guess you can make before you actually know which task it's coming from. And you see that for the first token, that it continues to get closer and closer to this midpoint task prediction, which is the best thing that the first token can do because it hasn't seen any examples yet. For the remaining tokens, it quickly moves away from this after this first stage to something else, and it learns to perform the tasks as we saw in the loss plots. Okay, so what's happening in the last stage? Well, similarly to what we saw for the M1 transformer, during the last stage, the loss on, let's call them out of distribution inputs, goes down. So if we have inputs that are larger than what you saw before. Yeah, so and that's related to here, right? So if we plot that, most of the inputs are sampled from some band, because normal distribution you sample from the surface of some hypersphere, and that moves away You get to predict for a wider band of x's. Okay. Yeah. So maybe the question to ask is why? Why are things moving the way they're moving? Especially for the last stage. Why is the thing that's happening during the last stage happening the way it's happening? So I propose it's all in the layer norm, probably. And the reason to see this is, again, so we have a picture of the transformer we're actually using here. We have, in this case, 2 attention blocks. There's a layer norm before the unembedding, which implements this thing. All right, so this is the problem. This is nonlinear. You subtract in the expectation value of the residual stream. This is computed across the residual stream. You divide by the variance. Well, the variance and the mean vary for different inputs. Right? So the noise from the inputs, as it ends up right before this layer norm, will change this prediction in different ways. So it acts as a kind of regularizing source of noise that makes the model predict things, I guess, less confidently than it could otherwise. So again, so now let's look at the embedding vectors for this. Where here I'm going to project the embedding vectors onto the subspace spanned by the 2 tasks. Right? What we see is, during this last stage, the embedding vectors collapse onto a line and one other point. That point moves away from the bulk and the line moves away in this direction. And so it turns out this line, well, the line going from the top left to the bottom right is parallel to the line spanned by the difference of the 2 tasks. And this point over here is moving away from this line along the line spanned by the, parallel to the line spanned by the task sum vector. So I should have put this figure here. So we've got one embedding vector representing the task sum vector, which moves along this direction. And then the remainder are spread along basically this line. And so that's what you see collapsing here. And this is related to changes, other changes happening in the model where a lot of the layer norms are collapsing. Well.
And what is this 1 dot residual stream?
It
moves away.
The 1 dot, that is precisely the component of the residual stream from which the unembedding matrix reads its prediction. Right, so the model uses this sum vector because it's the best default prediction, and then it modifies it later in the network using the projection along the difference vector. Okay. So I think I'll say a few words about what's next, which is, well, first of all, larger M, larger models. This is a whole family of transformers we have to inspect. At this point, I'm much more optimistic that we can do the rest. So I think, we've got sort of an intermediate M region to now probe, and the large M region, which is going to be qualitatively different algorithm, but probably something still we can understand and interpret. We need to look at larger models, a wider range of architectures. More mechinterp. So I have a lot of theories about what's going on here, but until you've sort of hammered it away with the correct ablations, sort of knocked out things and see that they're operating in the way you expect them to, I will leave that to the discussion speculation section, so come after and ask me about it. But yeah, so I think we can become pretty confident about what's happening in this model. And then the last thing is, this is also a test case for some of the other techniques we're developing. So covariance analysis, I haven't said anything about this because it's not working for this yet. We will get it working and see what it can tell us. Okay, so to summarize, right? We went looking in a system where we didn't know there would be transitions ahead of time, and all of a sudden we found a bunch of transitions. more than we expected. So they exist, they seem to exist. Some of these even seem to exist, seem to match some of the type A, type B classification that we've seen earlier. We can detect them.
I'll just add that you said there were transitions in Reventos et al., but to be clear, those are not transitions over training. So these are new transitions.
Yes.
We had seen.
Oh. These are new transitions, that's right. Not just transitions in hyperparameters, but transitions in time. Yeah. Tools we didn't think would be good enough seem to be good enough here. It's great. Less work for us. And we got more techniques coming. And I think we're pretty close to being able to understand this family of transformers exhaustively and not just be able to understand how it's implementing the circuits at the end, but the developmental stages it's going through and exactly what it's learning in each stage and why it's learning what it's learning in each stage. All right, let's get into this discussion. Jake.
I guess you did it the other order.